Do you see the PowerPoint slide? Now it's so. Is it okay now? It's I think full screen now. Okay, that's fine. So as I told you, I'm going to discuss the reinforcement learning to you in today's lecture because it's a very important the topic of the artificial intelligence or computational intelligence. However, the prerequisite of this course, you must know about the artificial intelligent agents, that how they work in the environment, how they may be developed. I try to give touch to them, but you have to study separately. So reinforcement learning is one of the hottest field right now. I mean, in this current age or current time, the reinforcement is a very important field. Therefore, that means that this field works in the works for the activation or for the development of the agents or artificial intelligence. Therefore, it is called the reinforcement learning is one of the hottest fields right now with the concrete applications growing at in incredibly what I say rapid pace from beating video games to robotics. Therefore, its essence, reinforcement learning deals with decision making. Now, decision making maybe means that it attempts to answer the questions of how an agent should act in a given environment. For example, there are different agents. If you are going to Mars or if you are living in some apartments and there are lifts and so on, so they are working like an agent following some instructions. So how you may control robotics or agents in the industries or robots or even there may be the soft agent and hard agent means software based agents and hardware based agents. So how they may be controlled, how they may be directed to get the what means to get your job finished properly. So we discuss this in today's lecture. Now, the reinforcement learning is a basically technique useful in solving control optimization problem. See, because of the evolutionary computation or the computational intelligence to provide you the optimized solution. Therefore, reinforcement learning technique is a useful in solving the control optimization problems. That what types of optimization problems here which may be faced by the different types of the agents, how they may be solved. So, what is the role of a reinforcement learning in that? So, by control optimization, we mean what is the control optimization? So, by control optimization, please stop your mic, mute your mic, please. If you mute your mic and write your question when I finish the lecture, you may ask the question. So, what is the control optimization? Means the job of the reinforcement learning is to solve the control optimize. Means this technique is useful in solving the control optimization problems. So, by control optimization, we mean the problem of recognition, the based action in every state visited by the system so as to optimize some objective function. Means to recognize the optimize action. Best action means optimize action. That is a solution. That is a proper action. So the average reward per unit time means how much time agent take to perform any action. However, there may be the different time. Means we may call it the random time. So the average reward per unit time and the total discounted reward over a given time horizon, it means. Yeah, these, how agent perform the job and what is the time level. So typically, RL means the reinforcement learning is used when the system has a very large number of states. Means at least it should be greater than 1,000 states and has a complex statistic structure which is not amenable to closed form analysis. Therefore, the basic idea is that of avoiding the learner. Now, learner means agent. Learner means agent because the reinforcement deals with the artificial intelligence based agents. So, the basic idea is that of avoiding the learner means agent for correct action, optimized action, best action, true action, and punishing wrong action. If means motivate means give reward on basis of the right actions and punish, improve. Punish means improve. It will not be you just say no. Improve it. So punishing the wrong action. If the agent is performing a wrong action, you have to improve that. As we, if you look at yourself, how you learned. Definitely, you learn from your environment surrounded by you. The first environment is your home. The second environment is your street. So you learned there. When you grow up in your childhood, you learned from home, you learned from your family members, you learned from your friends. Available in the street. How many times you were punished? Now that punish was not mean to, but that punish mean to improve your skills, to remove the mistakes. Initiatively, RL means RL reinforcement learning is a process of trial and error, which is combined with learning. It happens even in our life. So, means a process of trial too, and trial and error combined with the learning. So, the agent decides on the action based on the current environment state, and through feedback of terms means definitely agent what agent performs in the environment, it get the feedback. So if feedback in form of, so feedback in terms of or feedback in form of desirability of the actions, learns which action is the best associated with which state, means where this agent performs well, where this agent performs good. So the agent learns from interaction with the environment. This is the theme of the reinforcement learning. So while reinforcement learning is what I say is a general learning paradigm in artificial intelligence. This is so therefore different machine learning algorithms perform important role in the reinforcement learning, especially the neural networks play a very significant role in the reinforcement learning, and we discuss the neural network role in coming slides. So reinforcement learning is an area of machine learning concerned with the how intelligent agents ought to take actions in the environment in order to maximize the notion of the cumulative reward. This is the important cumulative reward, not the single reward. Means, an action performs different jobs, so at a different level, it may get different rewards, not the same rewards. So, for example, at the first job, it get the 0 point some rewards, but at second job, it gets the 1 point something, then 2 point something, then 0 point something. So, what will be the cumulative? So, the calculation by performing the cumulative formula, the what is the result? That is called the cumulative reward. So reinforcement learning is one of three basic machine learning paradigms, along with the supervised learning and unsupervised learning. Therefore, formally, if we talk about the reinforcement learning, formally it is defined that the reinforcement learning is the learning of mapping from situation to actions. Means draw the state, different several states, draw several states where agent has to suffer or agent has to travel and how agent will perform the action. So you reinforcement make these things states, and the actions taken by the agents are taken actions with main objective to maximize the scalar reward or reinforcement signals. So informally, if we talk about reinforcement learning, so informally, reinforcement learning is defined as a learning by trial and error from performance feedback from the environment or an external evaluator. So the agent has absolutely no clear knowledge of what action to take and has to discover, or you may call to explore uh, which action yield the highest reward. Therefore, means the reinforcement work in the mapping and mapping the states, different states according to job, according to the agent, according to requirement, and execute the ways and methods of what the actions. So the purpose of reinforcement learning is for the agent to learn. Means you this technique, this method, this model trains the agent to perform the work automatically. Means it generates the automation in the agent. So an optimal or nearly optimal policy that maximizes the reward function or other users provided a reinforcement signal that accumulates the what accumulates from the immediate reward. This is the purpose of the reinforcement learning. So basically, the reinforcement learning is also a learning technique. Therefore, we must know the machine learning. And I discussed machine learning, its techniques, its models, algorithms to you in my previous lectures. However, machine learning is a scientific discipline that is concerned with the design and development of algorithms that allow computers to learn based on the data, such as from sensor data or databases or from corpus data of any data, maybe data. So, a major focus of the machine learning research is to automatically learn to recognize complex patterns and make intelligent decisions based on the data. Therefore, machine learning performs on the available data. Now, data may be of any type. So there are different techniques. I just like the supervised learning, that is the task-driven technique. Means it works on basis of the classification. So it collects the data and splits the data in two sets. One is called the training data that trained the machine, that trained the computer, that trained the agent, AI agent, and another part is called the test data that test that either this machine or agent is working properly or not. And if it's working properly, then what is the accuracy level? Means what is the accuracy level of the model or the agent or the machine which is working? This is the purpose of the learning. So that's why it works. It's a task-driven technique or the model learning. Even you may call it a task. Means you define the task and then perform the supervised learning. So different models, different algorithms are here to use supervised learning and to solve the tasks. Another technique of machine learning is unsupervised learning. That is the data-driven learning. Means you do have a data. Without data, machine cannot work. So you must have a data. Data may be in form of different data sets or corpora or so on. So unsupervised learning is a data-driven learning. Means it makes the groups of the data. It segments the data. What you have, what type of the data you have. This in this technique, the data will be segmented into different groups. The commonly called the cluster means you have to make the clusters. Now different clusters. The model. There are different algorithms and models in the supervised algorithm learning that work on the clusters and analyze them, evaluate them, analyze them, and then get the result. And third technique, there are other techniques, but I discussed to you the important techniques. The reinforcement learning. This is also type of the learning. Otherwise, there are several learning techniques, the transfer learning, concept learning, and several others. But what is my topic is reinforcement learning. So I discuss you, and I have to come to the reinforcement learning. So reinforcement learning is close to human learning because agent works on the basis of human learning. Like we learn from the environment, from our birth to death, we are continuously in the process of learning. We learn different things. When we were child, our learning was limited. As we grow, we learn more, and now you are learning more and more. So this is a learning process which doesn't stop it till you are alive. So agents work like a human, and they learn like a human automatically. Therefore, algorithm means a learning algorithm learns a policy of how to act in a given environment. That is important. The reinforcement learning defines the policies, and agents works according to those policies automatically. Once policy is developed, then agent will work automatically. You see several reinforcement agents you may see, and they work automatically, but there's a policies behind them. So they learn according to that. Now, different policies, different action policies, different designing policies, and how to find the state, how to execute the action and so on. These are other problems, definitely. And the technicals, and we will discuss in this lecture on them, that how the designing may be done, how policies, what are the policies, how they may be executed. So every action has some impact in the environment. And the environment provides rewards that guides the learning algorithm. This is a reinforcement learning. So, dear student, a typical reinforcement learning problem, if you look here, this is a reinforcement problem. If you look, this is a reinforcement problem, and the agent receives the sensory inputs. If you look here, there's a learner. I told you learner means the agent, and it takes sensory input from the environment where it is deployed, where it is working. So it gets the sensory input from the environment, and means is a description of the current state of the perceived environment. So an action is executed upon which the agent receives the reinforcement signal or reward. So this reward can be positive or negative signals depending on the correctness of the action. So a negative reward has the effect of punishment the agent for a bad action. So if it performs the if it get the negative reward, definitely the negative reward will be punishment. Otherwise, if it's get the positive reward on this section, then it will work in a smooth. Therefore, agent receive, as I told here from this is the environment, working environment, it get the inputs and then perform actions. So it depend either it's a positive or negative. Therefore, reinforcement agent uh, has two important components: a trial and error search to find good actions, which forms the exploration component of RL, and a memory of which actions worked well in which situations. And this is the exploitation component of RL. Therefore, the action may cause a sorry. So the action may cause a change in the agent's environment. Therefore, uh, thereby affecting the future options and actions of the agent. So the effects of actions on the environment and future states cannot always be predicted. It is therefore necessary that agent frequently uh, monitors its environment. This is a very much important. Now we talk about the policies, reinforcement or other policies. So loosely speaking, all of RL comes down to either finding or evaluating a policy which is just a way behaving. For example, a policy could be playing a strategy in a class. That is also policy. So a policy takes a state, means how many states are there. So to take a state is basically policy. Like in the chess example, if you remember, in the chess example, the position of all the pieces on the board and assigns means look, all the positions on the board are basically states, and assigns an action to it means to assign an action means to move from one state to another state. If you recall the chess game, you look there several states, and to perform the action means move from one state to another state. Now there's a no fixed direction. Any direction may be used, but that is the action. So for example, given the state of your chessboard, the policy might ask you to move your queen forward. When you exit a state, you get some reward. So this is a very initiative. For example, if we use a happiness or pain to measure our reward as a humans, putting our hand in boiling water, like the exiting the superior state of having a comfortably cold hand will yield some pain, and thus a reward. That is a reward. So given a policy, we want to find its associated value function. Therefore, a policy, which is the decision making function of the agent. A policy is a basically decision making of the agent. And this function is used to specify which action to execute in each of the situations that the agent may encounter. Therefore, the policy is basically a set of associations between actions and situations, or alternatively, a set of the stimulus response rules. So, given a policy, we need some the reward function or value function and so on. So we want to find its associated value function. This means being able to assign a value to each state provided we follow some given policy. So, but what do we mean by the value? Do you know? So if we are in some state, the value of that state is simply the expected amount of reward that we will get from the state onward. So one of the important issue in RL, which occurs in the most search methods, is that of the exploration. Exploration trade-off, we may call it the exploration trade-off. That is an important issue. So RL has basically two important components, as I show here. These are the trial and error and the memory. So it is important that the agent exploits what it has already learned, such that a reward can be obtained. However, via the trial and error search, the agent must also explore to improve action selections in the future. Therefore, these two are important. I mean, the memory is important. How many actions you define, how many states are defined, and how the correlation and the actions may be connected to each other. So it's also important. Therefore, a policy, which is the decision making, as I told you already, function of the agent. So a reward function, if it means the policy definitely that is a decision function, but the reward function which defines the goal of the agent. Now, reward is given on the performance of the agent, output of the agent. Therefore, it defines the goal of the agent. That the reward function defines what are good and bad actions for the agent for specific situations. So the reward is the immediate and represent only the current environment state. Therefore, the goal of the agent is to maximize the total reward that it receives over the long run. And a value function value function is basically it specifies the goal in the long run. So the value function is used to predict future reward and is used to indicate what is good in the long run. As I told you that we want to find associated value in the policy. What is the policy we define for the agent? What we do, what we want to do, we find it's associated value function. So it means being given policy, defined policy. But what do we mean by value? If we are in some state, the value of that state is simply the expected amount of reward that we will get from the state owned. So optionally, in RL, agent may also have a model of the environment. Means the environment model mimics the behavior of the environment. So this can be done by the transition functions that describes transition between the different states. So if you look here, uh, uh, for the value function, if you look here, the value function is an important aspect is how the future should be taken into account. So a number of models have been proposed in this regard, like the finite, for example, the finite horizon model, uh, like the infinite horizon discount model, average reward model. So these models are defined to reach the target. So finite horizon model is basically in which the agent optimizes its expected reward for the next n and maybe any state of t for the time space. So in this steps, if you look here, even so here if you look here, the R of the time is the reward. R is for the reward. Reward is the reward for the time step t, or for the time step t. So the one function is that finite horizon model where the agent optimizes its expected reward for the next in of t steps. But if you look here, the infinite horizon discounted model, it takes the entire long run reward of the agent into consideration. However, each reward received in future is a geometrically discount according to a discount factor. Therefore, the discount factor basically enforces a bound on the infinite sum discount fund. So, and the third one is the average reward model. So the average reward model, which prefers actions that optimizes the agent's long run average reward. So these three models are used for the agents, and these three models show the reward system. So a problem with this model, if you look here, in this model, uh, is that it is not possible to distinguish between the policy that gains a large amount of reward in the initial phases and a policy where the large gain is obtained in later phases. So, in order to find definitely the optimal policy, it is necessary to find an optimal value function. Then optimal policy may be found. So, a value function should be there. So, now, model theory reinforcement learning, it's also important. Now, uh, I discussed here two things. One is the comparable difference learning. Second is Qlearning. I discussed to you. So temporal difference learning means when you first start learning about RL. When you are going to start learning about RL, chances are you begin learning about Markov chains, Markov reward passes, and finally the what Markov decision MDP means then definitely. So I am not going to discuss these things. You studied already, and if you need, you may study in detail. These are very important, and if you understand these things, you may understand different things of the computational intelligence, and especially the reinforcement engine. Because if I go for discussing on this, so time will be wasted. I don't. There is some limited time this lecture. However, if means when you first start learning about RL, chances are you begin learning about Markov chains, Markov reward process, and Markov decision process, MDP. So then you usually move on to typical policy evaluation algorithms such as Monte Carlo and the temporal differences algorithm learning. So in all of these cases, you have probably been working with the tabular representation of your state value because when the agent works in the state, so that like the grid, or you may call it the table as well. So table representation of your state, what states are there, and action value function, how action will be executed or performed. So this means that you were updating the value of the each state directly because in each state, the action value will be changed. Sometimes different value you may get. So in practice, this is quite impractical for MDPs with a huge number of states, or in the case where we are working with the continuous state spaces. So if I give you, if you are trying to guide a helicopter in 3D space, your state might be its current position. So velocity, angular velocity, acceleration, etc. So if you guess, there's an infinite amount of states, meaning that there's just no way of uh, storing everything in a table. That's why basically it's sometimes it's impractical for the MDPs. Now, what is TD or temporal difference learning? To one, so it's waiting on the relevance of recent temporal differences of previous predictions. But another technique that is very important, that is the Qlearning. So in the Qlearning, the task is to learn the expected discounted reinforcement values, means Q of S and A, taking actions A in the state is, then continuing by always closing actions optimally. So to relate Q values to the value function, like here, in this one. So the central idea in the Qlearning is to recognize or learn the optimal action in every state visited by the system, also called the optimal policy via trial and error. So the trial and error mechanism can be implemented within the real world system, commonly seen in the robotics. If you see the structure and working of a robotic, you may see this one. Or within a simulator as well, you are using the simulators for different purposes. So you may. So commonly seen in the management sciences, industrial engineering, even the your field as well. So in Q learning, the task is to learn the expected discounted reinforcement value, which I told you to of the state and the action of taking action in a state is, and then continuing by always choosing the action optimally. So you may relate by this one. So here the velocity into the state is the value, means what is the value of it's assuming that the based action is taken initially. So Q-learning rule is given like this one. So Q means what is the mechanism of Q-learning working? So agent chooses an action always on basis of the states, obtains feedback, and then when it chooses the action, then obtains the feedback for that action and uses the feedback to update its what uh, database where instructions are stored. So in its database, the agent keeps a so-called Q factor for every state action pair. So when the feedback for selecting an action in a state is a positive, the associated Q factor's value is increased automatically. While if the feedback is a negative, the value is a decrease because that is a paid reward, and the increasing is a good reward. So the feedback consists of the immediate revenue or the reward plus the value of the next state. Therefore, the trial and error mechanism of, if you look here at this figure, even the trial and error mechanism of RL shown here, the action selected by the RL agent is fed into the simulator, and the simulator simulates the actions, and the resultant feedback obtained is fed back into the knowledge base. That is the two factors of the agent. So the agent uses the RL algorithm to update its knowledge base because knowledge base becomes the smarter in the process and then selects a better action. So Q-learning feedback basically, the Q-learning feedback is a basically the feedback and is the equation. Usually, this is the lambda is equal to 1 by 1 plus R. R plus R means the reward. So the immediate reward is denoted by R here. This is the immediate. This is the feedback. Means what action performed by the agent, what type of the action agent is performed, and according to that it is get the feedback. So feedback is shown with the R, and R is I told you it's a reward. So R of I, A, J, and so where I here, if you look here, the I is the current state, is where agent performs the action or starts the action, and A, the action chosen in the current state. A is basically action which is chosen to perform in the current state I, and J, the next state means the next optimized state where action agent is to perform action or where agent is to go there. So the value of any state is given by the maximum Q factor in the state. Thus, if there are two actions in the state, the value of the state is the maximum of the two factors for the state. So, in a mathematical term, if you look at this equation, where lambda is the discount factor which discounts the values of the future states. So usually lambda is equal to 1 divided by 1 plus r, where r is the rate of the discounting. That what is the rate of discounting, and this r is basically reward. So, but if you look here at this figure, the RL algorithm agent that performs actions, and simulator, this is the simulator environment, and this is the feedback which I discussed to you here. So this formula I discussed to you. So we know, I discussed to you this one. Same, this formula is used, means trial and mechanism. The RL is shown by this figure. The action selected by the RL, this is means what is the action is selected by the RL agent is fed to the simulator. If you look here, fed to the simulator, and the simulator simulates the action and the resultant feedback to the obtained is basically in the this knowledge base of two factors. So the agent uses the RL algorithm to update its knowledge base, become the smarter in the process of the process, and then select better action. So now the neural networks and the reinforcement learning. Now, there are three learning methods: uh, PROP, and gradient descent reinforcement learning, and connecting Qlearning. So this one is if I talk to you in the Pero. So if I talk to you the neural networks and reinforcement, so neural networks and reinforcement learning have been combined in a number of ways. So one approach of combining these models is to use NN. NN means the neural network as an approximator of the value function used to predict future reward. That what will be the future reward of the agent, because agent future reward means what will be reward on the next state. So another approach uses RL, reinforcement learning means, to adjust the weights. So both these approaches are discussed in this right on this lecture. So like the P-rope means the uh, RP rope means the resilient propagation performs a direct adoption of the weight step using the local gradient information. So weight adjustments are implemented in the form of a reward or a punishment. So if the uh, means it performs good, the reward will be positive, and it performs bad, the reward will be the negative. So, if I talk about the RP rope, or we may call it the resilient propagation. Basically, I discussed propagation in the lecture on the neural networks, deep learning. So, back propagation, forward propagation, I discussed to you. So, I don't go to discuss again that what is propagation and how it works. But this is also the propagation, like the big propagation, with a very little different. So resilient propagation, in short, RPROP is one of the fastest training algorithm available. So RPROP algorithm just refers to the direction of the gradient. So RPROP, how it works means it updates the weight. So modern gradient descent variants try to what circums means what is the circumvent this problem by dynamically adjusting the adapting the step size. So our proof does this in a way that only requires the sign of the gradient. So by ignoring the gradient's magnitude, our proof has no problem if a function has a few various steps. So in the means, uh, we talk about the adapting the steps, how it adapt the steps, RPROP, how it adapt the steps. So in each iteration of the RPROP, the gradients are computed and the step sizes are updated for each dimensions individually. So this is done by comparing the gradients sign of the current and previous iteration. So the idea here, like the when the signs are the same, if signs are same, we go in the same direction as in the previous iteration. Since the this seems to be a good direction, the step size should be increased to go to the optimum more quickly. If you are going on the road and the signs are same, and then you will definitely go in a straight way. But if the signs change and if your direction is a change, definitely you will follow the sign to reach the target. Same agent will do that. So in the sign change, what happens? The new update is moving in a different direction. Definitely, agent will be updated with the new direction or different direction. So this means that we just jump over in optimum. So the step size should be decreased to avoid jumping over the optimum gains. This is the way. This is the method of adopting steps by the agent. So one advantage of the Arthrope is having a different step size for each weight. If one weight is already very close to its optimal value, while the second weight this needs to be changed a lot. So this is not a problem for Arthrope. Other gradient descent variants can have much more problems with such a situation, especially because the gradient magnitudes can be misleading here. So while Arthrope works well in a lot of situations, it is not perfect. For instance, Arthrope generally requires large ditch updates. So if there's too much randomness in stochastic gradient descent, then the escape size jump around too much and updates work badly, definitely. So the implementation of Arthrope is quite straightforward, and it should be to get a better understanding of our group, you should go for the vertical approach, like you may use the Python or the PyTorch implementation, even may be useful if you want to get more about it and want to be vertical work, you should go to the Python and make the programs or read the PyTorch implementation as well. This will help you in understanding this one. So now for the problems in the gradient descent reinforcement learning, for problems where only the immediate reward is maximized, means there is a no value function, only a reward function. So according to Williams, he proposed a weight update rule that performs a gradient descent on the uh, what? The gradient descent on the expected reward. So these rules are then integrated with the big propagation. So weights definitely are updated on basis of this formula delta WK. So on this formula where NKJ is the non-negative and NKJ in this one, the non-negative learning rate, and R of P is the reinforcement associated with the patterns Z of P. And entity of the K is the reinforcement threshold value, and the EKJ is the eligibility of weight of WKJ. So means the what I should say, the EKJ is the eligibility of the weight. In this, the eligibility of the weight is the probability density function used to randomly generate actions based on whether the target was correctly predicted or not in this one. So Thus, this neural network reinforcement learning rule computes GD in a probability space. And the Qlearning, connecting the Qlearning, so the neural networks have been used to learn the Q function in the Qlearning. So means that the neural network is used to approximate the mapping between states and actions, and even to generate the what generate the means generalize between the states. So the input to the NN is the current state of the environment. What the input is given to the neural network is the current state of the environment, and the output represents the action to execute. So if there are n of a action, then either one NN with the n of a output units can be used, or a n of NNs. So one for each of the actions can be used. Therefore, the NN is used to approximate the mapping between states and actions, and even to generalize between states. So if you look here, where do we need neural networks? So when we have a very large number of states in our map or in our environment where agent has to work, means then means the number of state actions appear. There should be, if you are designing the state, there must be the action, how action will be performed. Means you have to design both things. Either you have to design the, when you are designing the state, then you have to design the action. So this will be pair. So designing may be of how you design. Either you are describing means either you describe this what states means reduce the time. There the um, discretize the states. This is also one type of the designing. And how I mean when you have described it is discretize the states, then you have to define the actions, how action will be performed according to the states. So you have to define or determine the reward punishment. Then what will be the reward punishment? When you design the state and design the action, then you have to determine the reward and punishment rules, actions. That what will be the reward and what will be the punishment, and then establish the action policy. This is important. For this, when you design the actions, you must establish the action policy. So it is not, though it is not feasible to store the every two factors separately. However, in designing the actions, you must establish the action policy. Means how would you take the action? How the agent will take the action on the current and future state? Select the action. Definitely, selecting action is another way. That is not same. And the current state, that is another way of action, another type. And in the next state, the format of the action may be changed. So execute the action and another thing will be different. So how to take action? How to take the action in this? Either it would be random or fixed. So random definitely random in this way it is a good that you when you design the action, the agent will take execute the action in a different way for different states. Or you use some greedy action plans, means action with the maximum reward, or you may some others, or you may even go for the soft mix. Different action plans are here which you may take. However, it makes sense to store the Q factors for a given action within one neural network. When a Q factor is needed, it is a staged from its neural networks. Means when a Q factor is to be updated, the new Q factor is used to update the neural network itself even. So for any given action, means Q of the current action and the future action, Other this the action is a function of I, the state. Means this is the I is the state and the A is the action. So hence we will call it a Q function. And but the follows. So there are different things. For enforcement learning, we need definitely there are different ways. Either you are going to use the incremental learning process or using the batch learning process. So neural networks are generally of two types: batch updating and the incremental updating. Now it depends on the situations, on the states, on the policy of your actions. So the batch updating neural networks require all the data at once. This is a draw. This may be a drawback. Means you have to all take require the data at once. Since it may be randomized because the coming fire agent is going. At the current state, it find a fine environment, but on the next state, it find not a fine state. So the decision or the policy rule will be changed, or the policy will be changed. If you say you are going to make a security guard agent, definitely each state will be different for that agent according to security problems or a robot. So while the in this what happens, batch updating neural networks require all the data at once. But in the incremental update, what happens? So the incremental neural networks take one data piece at a time. So for reinforcement learning, we need incremental neural networks since every time the agent receives feedback, we obtain a new piece of the data that must be used to update some neural networks. So, if the incremental neuron or the incremental the algorithm for the incremental neuron, this is a simple algorithm. You do initialize the weights of the neural network at first. Then step 2A, compute the output of P using the output, and where the is the jth weight of the neuron, and Sj is the jth input. And the 2B in step 2B, update each step. What you have taken here, update it. So and in step 3, increment iteration by 1 means plus 1. So if iteration is less than iteration next, return to step 2 to perform this. So this the way to design the agents and perform the reinforcement, generate the policies, and find out the function value, the proper value, and way, for example, we discussed the Qlearning, uh, that how agent may be learned. So hope you got it. And if you do have any question, you may even ask. I will discuss to you. Okay, if not, then thank you very much. So thank you, dear students, for attending my class.